Welcome everybody. Today we will continue our discussion about the hydrogen production plant. Today we will discuss an important subject related to the shutdown and interlock system in this important unit. Hydrogen plant is connected to many units because it supply pure hydrogen. For example, it give the hydrogen pure to DHT, KHT, hydrocracking unit. Okay, so it's very critical and very important to you to understand the interlock system and shutdown system. Okay, the shutdown system protect the process because we have catalyst, nickel-based catalyst in the reformer tube. We need to protect against any damage or runaway reactions. Okay, so you will face a complicated circuits of loop inside the hydrogen production plant. I will simplify all the trip sections to you like in the form as like the following. Okay, first of all, the furnace flame detector. As we know, the hydrogen production plant, here we are here, the furnace flame detector. Hydrogen production plant work with huge number of burners, and for each burner there is a fuel gas supply and purge gas outlet from BSA. So you have two sources of this fuel gas going to each burner. For example, if you are working with around 84 burner for each one reformer or 100 burner for each one reformer, we have two sources for each burner for the fuel gas, like purge gas from the BSA and the fuel gas. If this flame detector for each row of the burner detect no flame, this is a burner management system like 4 rows or something like that off, there is a certain number for each reformer. If those number of flame, they will shut down the reformer and cause what we mentioned below. So the first important item you have to keep in your mind is the furnace flame off. What is the number of in your design, in your unit, in your refinery plant or petrochemical plant? When those burner are off, the reformer will trip and the unit will be shut down to protect the process. Process feed flow low, which is the natural gas in our case, and many hydrogen plant working with 2 steam to carbon ratio. Like if you are working directly with the natural gas low will trip the unit. This is easy to understand. But in many cases, you are working with feed like naphtha, feed like butane. Okay, so you have another steam to carbon steam injection point or mixing point, because you take the steam with this butane, you take the steam with this naphtha to mix point number 1, and go to methanator. This methanator will switch this stream into mainly C1. Okay, then you will be directed to the reformer. At this case, you will have 2 steam to carbon ratio and 2 mixing point. One mixing point for the lighter hydrocarbon with the steam, and the second mixing point will be with C1 with the steam. Okay, for this reason you have steam to carbon ratio low, when it will be around 2, the ratio between the CH4 and the H2O. If it goes below this value, it will trip the process. Okay, the combustion air van is the source for the combustion air. If you lose the combustion air, for sure you will shut down the reformer and you will shut down the process. Okay, and reformer furnace pressure high. Here we have a discussion here. Why? Because the huge number of burner and huge calorific value and the duty of the reformer will force the designer to make around 4 categories for the trip related to the draft. One with delay time 0 positive, so it will trip the reformer, and another one with delay time to give chance for the panel operator to take action, like for example plus 5 millimeter H2O and plus 35 millimeter H2O. This is 0 second and this is with delay time. This is in the positive. Okay, and as a surprise to you, in the negative also, in the deep negative, if this reformer working with huge amount of Q exposed to a huge vacuum, it will make trip also like minus 70 millimeter H2O 0 second or minus 30 with delay time. Okay, you understand? So because the reformer is huge and critical and handling a huge amount of Q, okay, thermal BTU, bridge thermal unit, maybe more than 20 or 30 million as calorific value dealing with this reformer, this huge amount of Q. So you have to shut down in the negative and in the positive, not like each normal heater you shut down with the positive only at one value. You understand this? The draft related to the reformer is critical. You have maybe 4 trip value related to this draft. Combustion air flow for sure low level trip, and the flow gas van trip, because in many cases when you are dealing with top fired reformer, you are working with balanced draft. For this reason, the flow gas van trip, it will trip the process and protect the process. Local panel switch for sure, if you remarked any overheating or fire case, you will shut down the process. Reformer exit temperature high, maybe the process temperature more than 875 or something like that, it will shut down the process to protect the outlet stream from the excessive heat, and for sure the power failure and instrument air failure. All this will activate the shutdown for the reformer and the process to protect the catalyst and the equipment. And what will happen after it will trigger the shutdown? Open vent between fuel gas valve, for sure the bleed, isolate process feed to the reformer, and isolate reformer fuel for sure, and close process steam to minimum stop value, because you have to insert more steam even in the trip case, okay? And stop the hydrogen compressor. If you are designed to work with hydrogen compressor, stop the PSA program and close valve inlet to PSA directed to flare or something like that, okay? This is the main interlock system related to the hydrogen unit.